Have you ever stopped and wondered what's really happening when a nail gets all rusty or when you bake a cake? I mean, it kind of feels like magic, right? Well, it's not. It's chemistry. And today, we're going to pull back the curtain on this invisible world and decode the language that describes it all.
So, let's kick things off with something we've all probably experienced, maybe a little too often. You leave a carton of milk on the counter, and a few hours later, it's, well, you know. But what is actually going on at a microscopic level to make that happen?
Or think about an iron nail. It starts out all shiny and new, but leave it outside for a bit and suddenly it's covered in that familiar reddish-brown rust. How does a strong piece of metal just transform into this brittle powder? And cooking. That's a great one. It's like this amazing culinary alchemy, right? Raw ingredients turn into this incredible meal with all new flavors and smells. But what's the secret behind that delicious transformation?
So you've got spoiled milk, a rusty nail, and a cooked meal. They seem totally different, but there's an invisible thread connecting all of these everyday changes. What is it?
All right, ready to get into it? Here's our game plan. First, we'll see how chemistry is literally all around us. Then, we'll learn how to spot a reaction, speak its language, and play by its rules. And finally, we'll see how it all comes together.
The answer is actually pretty simple. In every single one of those examples, a chemical reaction took place. The very identity of the substances involved has changed. And you know, this isn't just happening in your kitchen. It's happening inside you, right now, with every single breath you take.
Okay, so how do we know for sure that a reaction has happened? I mean, it's not like we can see the individual atoms rearranging themselves, but they do leave behind some pretty obvious clues. We just have to know what to look for, kind of like being a chemical detective. And here are the 4 main clues you want to look for. First up, a change in state. Think about a solid log burning and turning into smoke and ash. Second, a change in color, like a green leaf turning brown in the fall. Third is the evolution of a gas, you know, the bubbles in a fizzy drink. And finally, a change in temperature, like a fire giving off heat. If you spot any of these, chances are you're watching chemistry in action.
Now, describing a chemical reaction in a full sentence, well, it works, but it's a little clunky. It's like writing a whole novel when a short tweet would do the job. So, scientists came up with a shorthand, a universal language to describe exactly what's happening, nice and clean.
And check this out. We can take that long, wordy sentence in step 1 and boil it all the way down to that simple, elegant formula in step 3. That right there is the language of chemistry. It's the key to unlocking all its secrets.
But hold on, there's a catch. You can't just throw some symbols together and call it a day. Nope. You have to follow a fundamental law of the universe. It's a golden rule that can never, ever be broken. It's called the law of conservation of mass, and it's actually pretty straightforward. You can't create matter out of thin air, and you can't make it disappear. It's like playing with Legos. You can rearrange the blocks to build something new, but you always have to end with the same number of blocks you started with.
Okay, so this is where things can get a little tricky. An unbalanced equation like this one is called a skeletal equation. Think of it like a lopsided seesaw. On the left side, the reactants, we've got 1 iron atom. But on the right, the products, we have 3. The whole thing's off kilter. We need to fix it. You ready to balance this seesaw with me? It's kind of like a puzzle, and we use what's called the hit and trial method. So first, we list our atoms. Then, here's a pro tip. Start with the element that has the most atoms, which in this case is oxygen. We've got 4 on the right, so we need 4 on the left. Simple. We just put a big 4 in front of the H2O. Now the oxygens match. But wait, that gave us 8 hydrogens on the left. No problem. For step 3, we just go to the right side and put a 4 in front of the H2. Now we have 8 hydrogens on both sides. Almost there. Finally, step 4, we tackle the iron. 3 on the right means we just need to put a 3 in front of the Fe on the left, and we're done.
And there it is, a perfectly balanced equation. See those numbers we added, the 3 and the 2 4s? Now both sides of the seesaw are perfectly level. This equation tells the true story of the reaction, and it respects that unbreakable law of conservation of mass.
Okay, so now that we've got the hang of balancing equations, we can start to see the bigger picture. You know, not all reactions are the same. Some are slow and steady, others are like a fiery explosion. So let's check out the different families of reactions.
First up, we've got combination and decomposition, which are basically 2 sides of the same coin.
A combination reaction, on the left, is like building something with Legos. You take simple pieces, A and B, and you create something more complex, A, B. Decomposition, over on the right, is the total opposite. It's like taking that Lego model apart and breaking it back down into its original pieces.
Next, some reactions are like a cozy fireplace. They release heat and warm everything up around them. We call these exothermic reactions. Then you've got others that are more like a cold pack for an injury. They actually absorb heat and make their surroundings feel chilly, and those are endothermic reactions.
All right, next up is the displacement reaction. Here, a more reactive element basically swoops in and takes the place of a less reactive one. In this example, iron is more reactive, so it just kicks copper right out of its partnership with sulfate. It's kind of like a game of chemical musical chairs, where the most reactive element always gets the seat.
And finally, we have redox reactions, which are all about the transfer of electrons. But the easiest way to think about them is to just track the oxygen. Like it says here, when something gains oxygen, we say it's oxidized. When it loses oxygen, it's reduced. It's a constant chemical give and take.
And that brings us right back to where we started this whole conversation. That rusty nail, that carton of spoiled milk, yep, they're both examples of oxidation happening right in front of us. And now we finally have the scientific language to get what's really going on.
That rust on your bike? That's corrosion, which is really just the slow-motion redox reaction. And that funky smell from old potato chips? That's rancidity, another example of oxidation. And get this, the whole reason they fill chip bags with nitrogen gas is to push out all the oxygen and stop that very reaction from happening. Pretty cool, right?
You know, knowing a fact like that the sky is blue is one thing, but understanding why it's blue, well, that's a whole other level. And that's exactly what we've done today. We didn't just list facts, we explored the why of chemistry.
So, the next time you see something happening, a campfire, an egg frying, anything, don't just see it, understand it. You now have the tools to decode the secret language of chemistry. So go on, be a chemical detective, and see what hidden stories are unfolding all around you.